In this unit, you guys, is light and color. Now, light is a wave, right? In the last unit, we talked about mechanical waves. So in mechanical waves, they actually have to move a physical object, okay? If you guys take physics again, most likely you would take like a non-calculus-based physics class, and most likely it would be mechanics, okay? And this whole area of physics that we've studied, like up till now, is what we would call classical mechanics, and it just deals with actual physical things. Like I take a ball, I throw it in the air, right? I take some water molecules, some water, and I make them move up and down in a wave, all right? Now this is, we're leaving mechanics behind now, all right? So this is not mechanics anymore. Light waves aren't going to move some physical object. So a sound wave, it needs something to travel in, right? If I yell out in a normal room like this, right? The energy that's leaving my mouth, it has to vibrate air molecules, right? So there have to be air molecules around for you to hear the sound. If I pumped all the air out of this room, let's say we could survive, right? So if I pumped all the air out of this room and I tried talking to you, would you hear me? No, you wouldn't hear me, right? Because there's no air molecules to vibrate, okay? So the sound can't travel. Now light is different than that, all right? So light is a different kind of wave. Oh, I gotta reset this board. Don't quite know why that happens every day, okay? So light is what we call an electromagnetic wave. You may have heard of that. A lot of times we just say EM waves. That stands for electromagnetic. And we get to go back to our chemistry days. I know you guys like chemistry, right? Yeah, Mr. Gray, Mr. Vasquez, maybe Mr. Pi, right? So in chemistry, I want you guys to remember, in the atom, this is a very, very, very simplified version of an atom. You guys know atoms aren't really like this, but let's kind of think of the atom like this. So we have the middle part of the atom, that's called the what? The nucleus, thank you. And then we have, outside that, we have the electrons. And really the electrons are in, if you remember back to chem, they were in what we called the electron cloud. Do you remember that? Okay. So inside the electron cloud, we have these electrons. And then if you remember back to chemistry, I'm gonna make a little fancy drawing here. So let's say we had an electron, and they're in different shells. So the first two electrons go into 1s. Is this ringing a bell to you guys? Right? Going back to the old days. And then in the second one, it was the 2s, and then it was the 2p, and the 3s, and the 3p, and so on and so on. Okay? So let's kind of think of those electrons as being on springs. You know they're not really on springs. Let's just kind of think about it that way. So if I have something on a spring, like if I had a slinky, and I pulled the slinky out, right? Aren't I adding energy to the slinky? I am. It would be potential energy. Do you guys remember that? Because it's energy by position, okay? Well, it's the same, it would be the same with these electrons. So if I take these electrons and I pull them out, and I pull them from the 1s to the 2s, I'm giving them energy, okay? But if I pull the slinky out and I let go of it, what happens to the slinky? This isn't a trick question, you guys. So if I take a slinky, Isaiah, you're holding one end of the slinky, I'm holding the other. I pull the slinky out, right? Stretch it out. I let it go. What happens?
It goes back.
Oh, it goes back, right? So that's going to happen to the electron. So if I take this electron and I pull it from the 1s to the 2s, I'm giving it energy, right? But as soon as I let it go, it's going to pop right back down to the 1s, just like the slinky would, right? And so that movement is the source of electromagnetic waves. So electromagnetic waves, they all come from atoms, all right? And the cause of these waves is the movement of these electrons, all right? So it says they're caused by the exciting of charges. Well, those charges would be electrons. That's a negative charge. You guys, I know everybody remembers that too, right? Because the nucleus is positive, the electrons are negative. And when I say exciting, what I really mean is I add energy, so that's a chemistry term. These are all chemistry terms, right? So I'm adding energy and I'm pulling it out, right? So I'm pulling it, giving it, and that would be potential energy. So I'm pulling it out into the 2s or the 2p or whatever. I'm pulling it out to a higher energy level, and then I let it go. As soon as I let it go, it releases an electromagnetic wave, okay? Now, electromagnetic waves are also called electromagnetic radiation. We can use those two terms interchangeably, all right? They're also called, in general, light waves. So when a physicist or a scientist says light, a light wave, they don't just mean light that you can see with your eye, right? When we think of light, we think of light coming from like a lamp that we could see with our eye, right? But when a scientist says a light wave, they mean any electromagnetic wave. That could be a radio wave, it could be a visible light wave, it could be a microwave, it could be an X-ray, it could be a gamma ray, right? Those are all light waves. And that's probably the most confusing thing to students, that they're like, you keep saying light waves, but you really mean radio waves. Well, light waves are just electromagnetic waves, you guys, all right? So just so you know, those words are all used interchangeably. Now, this whole electromagnetic radiation thing. So let's talk about that real quick. I can't tell you how many times I've been to the store, right? And I'll go to the store, and people will ask the bagger not to scan their items, okay? Because they're like, well, that's electromagnetic radiation that you're using to scan my food, and I don't want my food to be irradiated, right? I don't want there to be radiation on my food. So, does anybody know what this word radiation actually means? It's okay if you don't. I would have thought your chemistry teachers would have taught you what it meant, but maybe not. I mean, if you had Garay, like, who knows what he did, right? So, this is what this word radiation means, you guys. All that it means is that I have something coming from inside of an atom, all right? So if I have a light wave coming from inside of this atom, then it's radiation, all right? Is all radiation harmful then? I'm going to give you a hint. No, yeah, it's not harmful, because the visible light that goes in your eye, is that harmful to you? It's not, but it's radiation. It's electromagnetic radiation. Radio waves, which are flying around this room right now because we have the Wi-Fi on, right? You guys, a lot of you take your cell phones and put them right up to your ear. You don't think that's a powerful EM radiation signal, right? We have, if I turned on the radio right now, I could tune it to any station because there are radio waves going through here. Those radio waves are electromagnetic radiation, all right? So not all EM radiation, well, most of the EM radiation is not harmful unless it gets super, super high energy. And you guys will figure out some of that stuff tomorrow, all right? So some, like gamma rays, you don't want to be zapped by a gamma ray all the time. Like a few, you're probably getting zapped every once in a while right now, just sitting here because they come from the sun and stuff. Or UV rays, you guys know that they can give you sunburn, they can do, things to you. But as long as it has less energy than ultraviolet, so anything from radio waves to visible light waves, it's totally fine, right? Totally not harmful. And you know what's funny is, hey, Mr. Hammond, could you let them in real quick? I pulled this ad, but I keep forgetting to put it in my presentation. Facebook keeps pushing this ad to me, which, by the way, Facebook is like the evil empire anyway. So, yeah, don't do social media. It's just a way for them to collect data on you. But anyway, I pulled this ad on Facebook that talks about a phone case. And it's a phone case that'll protect you from harmful electromagnetic radiation. And they keep talking about how your phone pumps out all this EM radiation, right? And you don't want it. Well, if I totally shield my phone from electromagnetic radiation, guess what? You can't make a call. You can't use the internet. You can't use Wi-Fi, right? Like it would be like a computer that wasn't connected to the internet at all. And by the way, you couldn't even look at the screen because the light waves are EM radiation, right? So I just want to make that point abundantly clear that EM radiation, EM waves, light waves are all the same thing, right? And not harmful. Don't get sucked into that trap. Okay? All right, so how do electromagnetic waves travel? Well, you guys, they're transverse waves, and they actually don't require an outside medium. So this is what I was talking about. This is where mechanics ends for us in physics, okay? Because the light wave doesn't need a physical object to vibrate. It actually carries its own medium with it, and that medium is a magnetic field. So these light waves travel through their own magnetic fields. And in fact, they travel fastest when there's no medium. Okay, so they travel fastest in outer space. Anytime there's a medium, it slows them down. And we'll talk more about that soon. So when the light goes from like outer space into air, it gets slowed down a little bit. When the light goes from air into glass, it slows down a little bit. All right? And once again, we'll talk more about this, but the denser the material is, actually the more it slows the light down. So the most optically dense material that we know of in the universe right now, there might be something different, but the most optically dense material that we know of is a diamond. It's the reason that diamonds are so sparkly. It has to do with something called refraction. We'll get there before the end of the year. All right? Now, can anyone give me proof that light waves can travel with no medium? So no medium would be like what environment? Right outside of the Earth's atmosphere? It would be like outer space, right? Can you give me proof that light travels through outer space? Really? Oh, the sun, right? Isn't the sun like way far away? And all that light travels through outer space to get to us, right? And then at night, when the sun's not as bright, we can't see the light from it anymore. If you look up, you can see all the other stars, right? Which are way, way, way further away than the sun. And we can see the light from them. So that's proof, you guys, that light travels through a vacuum, okay? It does not need a medium. And it's actually kind of the opposite of sound. Sound travels faster and faster as the medium gets denser and denser. Light travels slower and slower as the medium gets denser and denser because it has its own medium, it's cruising along in its own magnetic field. All right? Good so far? All right. So then all light waves, assuming they're in a vacuum, they all travel at the same speed. So that speed is very, very close to 300 million meters per second. Okay? So your book shows that it's 299,792,000 meters per second. Now, we're not going to use that. We're just going to round it. That doesn't bother you guys, right? It's like using 10 for gravity instead of 9.8. So we're going to round it. We're going to round the speed of light to 300 million meters per second. Now, the speed of light, you guys, if you ever see it written, it says it right here. C is the symbol for the speed of light. So C is the symbol for the speed of light. And we're going to make the speed of light 300 million meters per second. Or in scientific notation, that would be 3 times 10 to the 8th meters per second. All right, so that's all written up there. Now on your calculator, this is how it's going to look. It'll look like this: 3 with a big E and then 8. So when you put this in your calculator, make sure that you use scientific notation. I'm going to go over that again in a second. So 300 million meters per second. That's pretty stinking fast, right? So think about sound. Sound travels at 330 meters per second, roughly, right, at 0 degrees. And light travels at 300 million. It's a lot bigger, like a million times faster. Which is why, once again, remember, we can see the lightning before we hear the thunder. Because a light wave is traveling so fast, and even though the sound wave is traveling fast, not even close, right, to this fast. Yeah, so if the lightning was 330 meters away, or basically 3.5 football fields, it would take 1 second for you to hear the sound after you saw the light. Now, you've seen this symbol in an equation before, C, right? What equation? It's like the one physics equation every person on the planet knows. Really? Like, there might be a dude who had like my old hair. What was his equation? E. Are you guys doing this to me on purpose? Do you really not know? E equals mc squared?
There we go.
No?
Robert Hernandez has it.
Oh, nice. All right. So E equals mc squared, that C stands for the speed of light, right? If you guys have to take chemistry classes again in college, this is a big part of chemistry as well. And so they'll use C in their equations, right? So C stands for the speed of light. Are we good so far? Can I go forward? Isaiah, or can I go forward one slide? Or no? Okay. Okay, so I want everyone at this point to pull out their calculator. Whatever you use as your calculator. So if you have a TI, we'll do that one first. So you should be doing this at home as well. So this is how I want you to enter. I want you to push 3, all right? And then I want you to push this EE key. Now, it's located near the lower left. You guys see it? Do not push the small e. So it's capital E, capital E. Woohoo! We got our unit.
Whoa, nice. Get down.
Thanks, Mr. Voss. Just leave it there. I appreciate that. Yeah, and it's pretty cheap too. Yep. It was only $350 for that whole thing. $350, yeah.
Receipt says $498.
Well, that included the shipping. The shipping was $100.
Well, the shipping was free. On the attachment says shipping was free.
Because it's so bizarre.
Maybe come out upgraded us.
Maybe he upgraded us. I don't know.
Maybe.
He feels bad for me.
All right. Have a good one.
You too. All right. I'm sorry, guys. I got distracted because they brought in a tool chest for us. We're going to start actually putting things away again in here. So you hit that EE key and then you hit 8. All right. So what your calculator should show is it should show 3 with a capital E, 8. Right? If you hit enter on your calculator, if you don't have it in scientific notation mode, it'll change it back to 300 million. It'll put 3 with 8 zeros after it, right? So you want to use scientific notation, you guys. You don't want to try to enter all those zeros because I can almost guarantee you you're going to mess it up. And you also don't want to do like 3, hit the times button and the 10 and the exponent button and the 8 because I can almost guarantee it'll get messed up, right? So use the scientific notation. Now, if you're using your phone, you have to turn your phone sideways. And then when you turn your phone sideways, the EE button will appear right next to the number buttons, okay? So you'll have to push 3, that EE button, and then 8. And once again, if you hit enter, it'll put 3 with 8 zeros, okay? So that'll be 300 million. Use the scientific notation. It's your friend, all right, and use those buttons on your calculator. So now at this point, let's do a few problems. We're just going to do 3 problems, and then we're going to wrap things up for today. Make it kind of early. So I want to know, how far away is Mars? If it takes 3 minutes for a radio wave from the Perseverance, that's actually the Perseverance is on the fritz right now, right? Isn't that the one, Mr. Hammond?
I haven't heard.
So
I was watching cover news.
yeah, the Perseverance is a probe on Mars that's testing. I think that's the one that's testing like for seismic activity inside Mars, and it's getting coated with dust. All right, but otherwise, what happens is we send instructions via radio waves from Earth to Mars, and then the Perseverance sends us its signal back. Those signals take 3 minutes to travel. All right, so how far away is that? Well, we know a few things. It looks like we hardly know anything in this problem. So the very first thing we know in this problem is we know the time. So the time is 3 minutes. We don't use minutes, we always use seconds. So how many seconds would that be? 180. So the time would be 180 seconds. Now we're trying to find how far away. That's distance, right? And we actually know one other thing. We actually know the velocity, because light, if it's traveling in a vacuum, always travels at 300 million meters per second. So in our calculator, we're going to enter that as 3e8. Now, if I have d, v, and t, I'm going to use the very first equation that we learned on the very first day of physics, which I kept promising you we'd be using till the bitter end. V equals d over t. So the velocity, 300 million, or we're going to enter it in our calculator as 3e8. The distance we don't know. Time is 180 seconds. Oh, I dropped my units there. It's supposed to be meters per second. Now I want to solve for d. I told you guys, like, a lot of you are best at doing cross multiplication, so I'm just going to do it that way. So I'm going to cross multiply d times 1. That's just going to be d. And 3e8 times 180. Can someone put that in their calculator for me and then give me an answer? My guess and check is going to be 5.4e10. Let's see if I'm right.
Sure.
I'm right. And you guys, it's because I remember math rules, right? Because that would be the same as 1.8 times 10 to the second. And when you have 2 exponents, you can add those and then multiply these numbers. Or you could just enter it in your calculator, right? So it's going to be 5.4 times 10 to the 10th meters away. Or another way of saying that, so it's going to be 54 billion meters away. 54 billion meters away. So Mars is pretty far, right? Have you guys seen The Martian, by the way? With Matt Damon in that movie where he gets stuck on Mars? No?
I think so.
So in The Martian, they're trying to talk to each other, and it's the same thing. There's like 3 minutes in between each message, at the very least, depending on where he's at. Sometimes it's even longer, right? Okay, so let's go on to the next problem. So now,
Jasmine says she loves that movie.
oh, I love that movie too. My wife and son just watched it for the first time not too long ago.
We watched it too, right?
Yeah, we watched it in movie club, yeah. All right, so if it takes 8 minutes and 20 seconds for light to travel from the sun to the earth, how far away is that? So just so you guys know, that's not a made-up number. It takes 8 minutes and 20 seconds for the light to get from the sun to the earth. So if for some reason the sun turned off or blew up or anything, you could happily live your life for almost 8.5 minutes before, the lights turn out, right? Should make you happy. You get extra time. That's not going to happen, by the way. We're going to be all right. So this is very similar to the last problem. We have time.
We don't know.
Huh?
What if it already did and we're just waiting?
Oh yeah, right. And then we get to spend our last 8.5 minutes doing physics. That would be the best.
Calculating how long it would take. That would be
So the time is 500 seconds. that would be 8 minutes, 20 seconds, right? We know velocity. The velocity is 300 million meters per second. And I just need to know the distance. So we're going to do v equals d over t again. And we'll plug everything in there. So we have v is 300 million. The distance, we don't know. And the time is going to be 500. So we'll do the same thing that we did before. We'll cross multiply it, right? D times 1 is just D. And 500 times 300 million is going to be 1.5 times 10 to the 11th? Yes, all right. And that would be meters. So that would be 150 billion meters away. Pretty far, right? Sun's pretty far from us.
How much would that be in feet, actually?
150 billion
Like,
times 3.2. So it'd be like close to 500 billion feet, right? I mean, the sun's really far. And the reason that we can see it in the sky and it looks pretty reasonably big is because it's ginormous, right? The sun is like 99% of all the mass in our solar system. So if you took all the planets, added them all together, they're 100 times smaller than the sun. So think about it that way. It's kind of crazy.
AKA ginormous.
AKA ginormous. That's a technical term, by the way. All right, last problem. After this one, I'll cut you guys loose to work on your practice problems. So light has a wavelength of 4 times 10 to the negative 5th. Okay? So if the length of a wave, otherwise known as lambda, right, is 4 times 10 to the negative 5th, that's 4e negative 5 now. Okay? And we know that the velocity of light is always going to be 300 million meters per second. I want to know what is the frequency of the light. So our wave equation from last time, we're still going to use it. So I promised you guys I wouldn't give you any new equations, but we get to use our old ones. So we have velocity of a wave equals frequency times wavelength. And then we're going to stick everything in here. We have 300 million meters per second equals the frequency times 0.00004 meters. So I'm going to divide both sides by 4 times 10 to the negative 5th meters. That'll get rid of that. And my guess and check here is 7.5 E12. And that would be hertz. I left off my units. Is that right?
Yeah.
Woohoo!
that is right.
I haven't lost my touch. My guess and checks were easier today. Easier than you guys realize, right? If you forget about exponents. So that stuff in math class, it's actually useful, right? It is. And if you go into science, any scientific field, you're going to use it all the time. So does it sound good? Make sense? So if you go onto the daily agenda, there is a practice problem set that I want to say has 7 problems, only 7. So that's, those are the practice problems for today. First homework lottery assignment for this unit. And then, Mr. Hammond and I tightened up this unit so that we will test on Wednesday of, not next week, the week after. All right, so we have exactly, after today, we'll have exactly 10 more days of this unit. Sound good? And then the seniors, like everybody starts leaving soon. Seniors have 17 days left. Juniors have 22 days left. And then, then I have to cry a tear every day until I get to see everybody back in school. It'll be like 90 days over of summer vacation. I don't know if I can handle it, right?
That's a lot.
I don't know what you're talking about.